This lesson is about transformations of the graph y equals x squared, and in particular looking at what happens to the graph as we vary the values of a, c and d in this form of the equation y equals a, x take c squared plus d. So we'll start with y equals x squared. We take some x values from -3 to 3 and square them, and then we'll plot these as pairs of coordinates and then draw a nice smooth curve through the points to give the parabola y equals x squared. So in our first transformation we'll plot the graph of y equals x squared take 3. So to work out the y values I need to subtract 3 from each of the x squared values. And now my pairs of coordinates are -3, 6, -2, 1, etc. And again, once we've plotted the points, we join them with a nice smooth curve and label this one y equals x squared take 3. And you can see that the transformed function is the same shape as the original, but it's translated down 3 units because of this subtract 3. In our second transformation, we're going to subtract 5 from each x value and then square that result. -3 take 5 is -8, squared is 64. -2 take 5 is -7, square that. -1 take 5 is -6. Now it seems we haven't reached a turning point yet, so I'm going to add a few more x values. 4 take 5 is -1, square that to give 1, 5 take 5 is 0, 6 take 5 is 1, square that to give 1, 7 take 5 is 2, square that to get 4. So these large y values are not going to fit on the same axes as before, I'm just going to plot the ones near the turning point. So I can plot 2, 9, 3, 4, and so on. And once again I'll draw a smooth curve through these points, which I'll label as y equals x take 5 squared. So this curve is also the same shape as the original, and it's translated, but this time horizontally. It's translated 5 units to the right. With our third transformation, I'm going to use 2 rows of the table, x take 1 squared, and then plus 4. So for this row I'm going to subtract 1 from each x value and square the result, and then I'm going to add 4 to each of these values. So not all of these are going to fit on my axes, but I'll plot the ones that do. So -1, 8, 0, 5, and draw a smooth curve through the points. And you can see that this transformation is also a translation from the original, 1 unit to the right and 4 units vertically upwards. Finally, I'm going to plot the graph of y equals 2x squared plus 3, and again I'm going to take 2 rows of the table to do this. Firstly, double the x squared values and then add 3. So doubling the x squared values gives 18, 8, 2, 0, 2, 8, 18, and then adding 3, 21, 11, 5, 3, 5, 11, 21. So plotting the ones that will actually fit on the axes, we'll start with -2, 11, -1, 5. And hopefully you can see, even before I draw the curve, that this one is different from the others. It's a different shape. It's been stretched because of doubling the x squared part of the function. So I'll draw the curve on. We can see that the curve has been dilated by a scale factor 2, and it's also translated vertically upwards. But it's important to get the order of these transformations correct. If we were to first translate the curve 3 units upwards, dilating stretches the curve away from the origin. if we translated the turning point would move to 0, 3, but dilating would move that turning point further away from the origin up to 0, 6, and then move all of the other points after that. So what's happened in this case is the dilation has occurred first, and dilating y equals x squared means that every point is stretched away from the x-axis. So 0, 0 stays in place, but negative 1, 1 moves to negative 1, 2, negative 2, 4 moves to negative 2, 8, and then the curve is translated 3 units vertically upwards. Now I want to bring us back to the general form of the equation, y equals a x takes c squared plus d, and identify the values of a, c and d in each of these examples. So in the first example, a is 1, c is 0 and d is negative 3. In the second example, a is 1, d is 0 and c is 5. In the third example, a is 1, c is 1 and d is 4. And in the third example, a is 2, c is 0 and d is 3. So what do a, c and d transform from y equals x squared? Well, when d is negative 3, the function translates down 3 units. When c is 5, the function translates right 5 units. When c is 1 and d is 4, we translate 1 unit right and 4 units up. And when a is 2 and d is 3, we have a vertical dilation parallel to the y-axis, scale factor 2. That's that stretch upwards away from the x-axis. And then a translation 3 units up. So let's summarise the effects of a, c and d. Given a function in the form y equals a x takes c squared plus d, compared with the quadratic equation y equals x squared, this function has a dilation scale factor a parallel to the y-axis, a horizontal translation c units to the right, and a vertical translation d units up. Now in our example we had y equals x squared take 3, so notice that the value of d here is negative 3, and therefore our function translated 3 units down. In our horizontal translation we had y equals x take 5 squared, and so we went 5 units to the right. But what if that was y equals x plus 5 squared? What's the value of c there? Well, notice that in the general form it's x take c, not x plus c. So if we rewrite this as y equals x take negative 5 squared, that would give a value of c of negative 5, and therefore it would be a translation to the left instead of to the right. I'd just like to demonstrate how technology can help us to explore some transformations of functions. This is a screenshot of graphing software, and the black curve here is y equals x squared. The blue curve is y equals a x takes c squared plus d. And with the constant controller here, I can alter the values of a, c and d. So at the moment, a, c and d all take the value of 1, and you can see the turning point here is at 1, 1. So this blue curve has translated 1 unit to the right and 1 unit vertically upwards. But I can alter the values of these constants to see what happens. So I can change the value of d to 3, and I can adjust that value in steps of 0.1. Or I can change the value of c or the value of a. This is with a equal to 2, so you can see that vertical dilation. So Autograph is available for a free 30-day trial, and I would recommend downloading it so that you can explore without having to manually plot the graph every time. Finally, because we've been working with parabolas in this lesson, I would just like to spend a few moments looking at a key feature of parabolas, which is the turning point, and see how the coordinates of the turning point relate to the transformation of the function. So in our original parabola, y equals x squared, the turning point is 0, 0. In y equals x squared take 3, the turning point is at 0, negative 3. In y equals x take 5 squared, the turning point is at 5, 0. In y equals x take 1 squared plus 4, the turning point is at 1, 4. And in y equals 2x squared plus 3, the turning point is at 0, 3. And hopefully you can see that the turning point for each of these functions in terms of a, c and d is given by the coordinates c, d. And that's why this form of the quadratic function is known as turning point form, because it's easy to read the location of the turning point without having to plot any coordinates.